All right, welcome to episode 8 of Bit by Bit. In this episode, we're going to cover chapter 5 of the book, Assembly Lines. Particularly, we're going to be looking at loops, more loops than we learned before, and some new branching and a new firmware call, and we're going to learn about paddles. It's 9 packed solid pages that took me a little while to understand and even longer to produce a video of, because the first few attempts were miserable. Very difficult parts that I thought I understood till I got to explaining them, and then that was not good. So here, hopefully this video is a little pretty refined. All right, without further ado, let's just get in and review what we know. So we know some operations already, instructions, mnemonics for assembly code, and there's 15 instructions. And we're going to kind of go through them a little different than we've been looking at them in the book and stuff. So you'll notice that they're in pairs, and there's symmetry here. There's sort of a flip side to things. These are orthogonal to mostly, but we have this instruction jump to subroutine, and it's corollary, it's mirror the return from subroutine. That's nice. There's a pair, very useful. And then we have the pair load the accumulator and then store the accumulator. Load the X register, store the X register. Load the Y register, store the Y register. All right, so 6 new instructions that we learned in the second episode or something, third episode, somewhere around there. But anyway, 6 new instructions. And really, there's only one form. It's like we load something and we store something. But we got 3 registers to do it with, so we get 6 instructions. Next up, we got increment and decrement. These work on memory locations. And then we have increment X, increment the X register, decrement the X register, increment the Y register, decrement the Y register. Now the 65CO2, which is the enhanced CPU, microprocessor, whatever they're called, the heart of the machine. The original 6502 does not support incrementing the A register, but in the enhanced CPU it does, but we're going to stick to straight up 6502. So these 2 instructions are working on memory, but there's mirror image, right? You can increment it or you can decrement it. And the same thing for the 2 registers, the index registers. And then we have this thing called branch not equal, our first branch instruction. And it makes you wonder, what's its mirror image? And if we just think a little bit, branch not equal, there's probably a branch equal. And there is, it's BEQ, and we'll learn it in this episode. But there's generally always going to be some kind of a parity between these. And so when we learn one instruction, we really learn 2, or we learn them together so that we can do those things. Then I followed a guy named Don Lancaster who wrote some brilliant books back in the 70s that I read a couple of years ago, or maybe even less, maybe last year. They're just astounding. One of them is called the Microprocessor Codebook or Microcomputer Codebook. I don't remember which. It comes in 2 volumes, and it is brilliant. Go buy it. You can find it. Otherwise, download the PDF. But in it, he talks about creating flashcards for instructions. So here's some flashcards. I got this one for JSR, and then I got one here for the load the accumulator. And you'll notice that they're a little different. The JSR one hardly has anything, and the other one is jam-packed. But by writing them all down, I have a much better sense of how they work. And so I created 21 of them. To go with all the ones that we learned through today. And so what do these cards look like? Let me go ahead and give you a couple examples. Start with the JSR, jump to subroutine. You put the opcode in the upper left corner. You put a description so you can remember it. This comes straight out of the book. The appendix of Assembly Lines has this, and the 6502, what do you call it, data sheet would also have it. And then we drop down a line and put flags, and there's 7 of them, and they're not affected by this jump to subroutine call, so they're all dashes. Then I go in here and I'd say, what does it do? And this again comes from the book, I didn't make it up. Program counter +2 gets put on the stack, so the current instruction +2 skips past the current instruction to the next one. That goes on the stack. And then program counter plus, or the last byte of the current instruction gets put on there. When it's returned, it gets popped off an increment. That becomes the new program counter. So then it takes the program counter plus 1, which is the byte after the opcode, puts that into the low byte of the program counter, and then takes the one that's 2 bytes past the opcode and puts that in the program counter high. So if this is our opcode, 20, and then there's 2 bytes of location, like DD, FB for the bell, right? The DD part goes into the program counter low. The FB goes into the program counter high, and then that's where it jumps to, right? So that would jump to the bell. Anyway, it has a mode. There could be many modes. In this case, there's only absolute mode, and it's referenced, the way we call it is JSR, and then some operand, like $300. That's how we did it for our code, or $FBDD for the bell, etc. And then there's the opcode. It's always 20 for JSR. There's 3 bytes. There's the 20 and then 2 bytes for the address. And it takes 6 cycles to do all this work. 6 microseconds, if you will. All right, here's another more involved example, but probably the most involved example. So it's usually your card is going to be somewhere between these two, and often pretty much on the minimal side, but occasionally it's going to be longer like this. But this is LDA for load the accumulator. It is concerned with or conditions the flags negative and 0, depending on what gets loaded in. And it gets it from memory into the accumulator. There's a bunch of different modes. There's a note down here about adding one when the page boundaries cross. Then we look over here and we can see that that just increases the number of cycles. So we can ignore that for now because we don't care. And then there's a mode, a form to the instruction, which is kind of its syntax, an opcode, which is the byte that tells you that you're dealing with this type of mode of this instruction. There's the number of bytes that this instruction takes in the machine code. So we'll look at that in a second. Then the number of cycles it takes to complete the operation. So with the load the accumulator, oftentimes we're going to do it immediately, like LDA pound 13, okay, which means when we type that, really what happens is we get A9 and 13, 2 bytes. That's what that means. A lot of times, though, we might use an absolute address, like if we put it into, like we're going to do today, we're going to put one at address 0006, which is at the page 0, but we're not going to reference it as page 0. We're going to use its absolute address. And we're going to say LDA $0006, and that's going to convert to AD 0600, because 6 is the least significant byte. And it takes 3 bytes because AD 0600 is 3 bytes. And that way we can kind of instantly know, kind of like having the book, but we just pull up the card and go, oh, yeah, which one is it we're doing? We're doing absolute. Yeah, absolute. That's AD, and it takes 3 bytes. So AD, low byte 06, high byte 00. Yay. That's all there is to it. So hope that's useful to you. And I highly recommend you do them all. There's only 56 instructions to be done with it. So you get 56 cards and you've got your Apple IIe 6502 reference that you created. And that's good stuff. But in this lesson, we're going to do this. We're going to learn BEQ, which is branch equal, which goes with our BNE that we knew before. We're going to learn jump, which is unconditional jumping. Begs the question, what's the flip side of jump? I don't know. All right. I kind of, in my twisted brain, think it's no op, NOP, but that's not, surely that's not right. But we don't know what it is. We'll just hold it out and think, well, it ought to be something, because everything else is going to be something, almost everything else. So then we get this these instructions here, tax and tay and tuxan, tawa, whatever these are. They're transfer from the accumulator to the X register, or transfer from the X register to the accumulator. This is a way to move between the X and the A, and between the A and the Y. That's all it is. Once we've done this, with just these little additions, we're going to have a third of our instruction set, just like the author talks about, which is pretty impressive given that this is only like the third assembly lesson in the book, but it's pretty impressive. And it's fun. So let's do this thing with the setting up paddles, because we're going to use the paddles. And once we set up the paddles, our emulator is going to behave strangely. So we're going to set it up with an eye towards unsetting it up, because you'll see. So here we are in the emulator, and I'm going to go to the joystick thing, which now I kind of understand why it says joystick, and it's the settings. And inside of here, we're going to look at the input tab, and we're going to look, and this joystick 1 is probably already set to keyboard numpad right now, but we want to set it for the mouse, okay? And joystick here is going to be the same as paddles. And they are two different devices, but Apple doesn't know which one you're using. It just reads them they just wind up kind of having different values and operate differently, but they come in on the same port, I guess, if you will. All right, so, and wow, I say that like I know, I'm just guessing. But what we can do, what I do know, is we can set it to mouse, and then we read this configuration thing really carefully, especially this bit at the end, because otherwise we're stuck in mouse trap mode and we don't know how to get out. So we say to end the joystick emulation and regain the mouse cursor. Apparently it's going to capture the cursor. Click the left mouse button while pressing control. So remember, you got to press the mouse button and then you press control, all right, to get out of it. And so we'll say okay here, and we'll do this. We'll say okay. Once we click into the, let's say we start the emulation, and I don't have any disks loaded, but let's say we start the emulation. And then I click in here, it traps the mouse, and you can see that it's doing something weird with the mouse. We don't quite know what, but it's definitely doing something with the mouse. Remember, to get out of it, you press the left mouse button and the control button. Left mouse, control. There we go. Maybe it's control and mouse, even though it said that. Whatever. You see, I got my mouse back. Yay. Okay. So for right now, until we get to that part, we're going to turn it off because it is really annoying. We can put it to disabled or keyboard numpad. Let's leave it the way it originally was. And now when we click in here, it doesn't affect our mouse. All right, so we've set up paddles for later, learned how to do it, and then we turn it off. Okay. Next up. And we are doing swimmingly on time, so good. We'll do the loop in basic, and then we'll redo the loop in assembly and kind of compare and contrast. So I have nothing loaded on the floppy drives, but we'll go ahead and load up Merlin. So Merlin 8, 248, DOS33, that's the disk. And then we'll have a work disk as well. You know what? Maybe I think I will make a new blank disk. So I'm going to go into where I store these sort of things, and we'll take the blank disk that I made some time back, and we'll just copy it over. We'll call it Merlin 2. All right, and then we'll call this Merlin work 1. All right, so we're going to use this Merlin work 2. We're already on disk 2. All right, there, Merlin work 2. Okay. And so once we load it up, it booted it automatically. Who cares? I'm going to change the drive to that work disk and do a catalog just to see that there's nothing there. Yay. And then I'm going to go and I'm going to quit. So we get back to the basic prompt, and I'm going to type this basic loop. And what we're going to type is exactly as it says. Home, oops, I'm going to have caps lock on, home. Yep, 20x equals, and then I think it started with 255, so we'll just do that. You know what? No, we want to stick with the 10. I kind of tricking your chain a little bit, but we're going to reference back one of the other videos that I did recently, which was the escape mode. I'm going to go ahead and fix this. Going to set it back to 10. So I had escape to go into escape mode. Changes to a plus cursor, but only when I'm in like DOS 3.3. When I'm on a regular basic, it won't change to a plus, but it works the same way. So you hit escape, you go up to the first digit of the line number you want to change, hit space, it goes out of escape mode, arrow over to save those characters to the left into the buffer, and then I can just type here, 10. I don't have to get rid of the 5 because it's under my cursor. Only the stuff that I'm left of my cursor is going to get saved. I hit enter and it disappears, and we can list to see that that's the case. Fine. Moving right along. 30. Print X. 40. Oh, and before we get there, let's think about what we've done. So 10 home clears the screen. 20x equals 10 is our initialization of the control of the loop. So we init here. Line 30 is doing some work, and line 40 is going to do an increment, in this case with a -1. So we're going to increment by -1, subtract 1 effectively. And then 50 we're going to test. And if x is 0, which is different than last time, then we're going to go to, and the go to is totally optional. You can just type then 70, but this is more explicit. And then 60, we can go to 30. And 70, we end. Let's list and talk about it. All right, so we have the homing of the screen just as housekeeping, sweeping it clean. And then 20, we're going to initialize a control variable. And our control variable is called x. It's how we're going to know we're getting done. And we're going to set it to 10 because it's going to do it 10 times. Or almost 10. You know, it depends on how we do the test as to whether it gets 10 of them or 9 of them, or 11 for that matter. But here it goes. We go to 30. We're going to do some work. So print x, that's our work. 40, we're going to increment, which is x equals x minus 1. And then we're going to test. If x is 0, then go to 70, which doesn't print it out. And then, but if it's not equal to 0, then it's going to go drop down to 60 and then go to 30 and print it. Subtract another one, test again, and so on and so forth. So it's going to print 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. But if it gets to 0, it's going to skip the printing part and just go to the end. All right. So that's how it's supposedly going to work. Let's run it, see what happens. 10, 9, 8, yeah, through 1. All right, it worked. It's beautiful. Now we want to do something similar in assembly language. All right, to get back to the assembler, we're going to do ASCCM. And we're back. We're still on drive 2. Let's edit some source. And we're going to edit source just like this right here. Pretty much. Yep, we got 10 already here. So let's do it. I hit E for edit, A for add or append. This is different looking than the line editor. Let's cover it. It's covered in one of the previous videos, but let's cover it briefly here. We're in insert mode. If we want to switch to override mode, we hit tab. The I goes away. If I want the I back, it's Control I. Okay, and that's that. This line right here is a good guide for when you should end your line. If you go beyond it, things are going to wrap. They're going to look funny. They're going to work weird. Don't go too far past it. And probably don't go ever past it if you can avoid it. And then what line we're on? 1. That's what that means. All right, so to get the line of asterisks like we had before, where we would do Control P in the line-oriented one, we're going to do Alt-8. That gives us a line of asterisks. And then to get the boxy thing, like space Control P, we're going to do Alt-9, which is going to put the box in. We're in insert mode, so if we start typing now, you can see that we push the box, which isn't really ideal. So we'll turn overstrike, we'll turn the insert mode off, and we'll do overstrike. So without further ado, let's see, how do I do that? Tab. That takes us out of insert mode. Then arrow over to here, we'll Control D to delete these guys. All right, now we're back to a normal box and we're in overstrike mode. So we can hit space, another space, or 2 or 3 or 4 or whatever. We can type loop 2. We'll just call it loop. All right, and then enter, and then Alt-8 gives us another line of those, and this is going to be our code. We hit asterisk, another asterisk, and this time we're going to space over here somewhere, type obj $300. This used to be helpful. Maybe another space over here. Oops, yeah, we're in overstrike mode. 300. Wow. This used to be helpful and required, but now it is not allowed. And so we're just going to leave it in as a comment. Then we're going to put the org. And when we do this, we're going to kind of note a couple of things. One is we hit space. It isn't a text editor. This looks like a text editor, acts like a text editor a lot of time, but it's not. It's an assembly language. It's an assembler that has an editor. So it's focused on that. So it has fields. First field is the label. The second is the mnemonic. The third is the operand. And the fourth is for comments. So we hit space once, and we're where we type mnemonics. And we hit space again, and that's where we add the operands, 300, and we could put a comment if we wanted to. But you'll notice that we're off on alignment. So right now I'm in overstrike mode. I'm going to hit Control-I to go back to insert mode. And then I'm going to space that over so it lines up. And I'm going to space that over so it lines up too. And we'll leave it in insert mode until we don't need it, and then we'll move it out. But let's see. We're going to type home, a space, EQU, which is equate or equal. It's equate. But we're going to equate this location, FC58, with the label home. So FC58, which is just the address in the monitor ROM of the home to screen function. Then we'll hit asterisk and blank line. We'll type start. And then JSR, which we already know, jump subroutine. We're going to jump to what subroutine? We're going to jump to the home subroutine, which is in monitor ROM. And we'll let that do its thing. And then I'm going to load the X register from this immediate value of 0A, which is 10. And it's 10 in hex. All right, and then yeah, now we can use a comment. So I space over to the comment field and I type in, this is the initialization of my control variable. And then we'll loop, store the X register into the location absolute 700, which is a screen location. It'll print up here somewhere around here. It'll print our output. It'll do it so fast we can't really see it, or we can't even see it, but we'll see the result. And that's really our loop doing its work. And then we'll decrement the X register, which is our increment. And then we'll branch if equal to the end. And we'll call that the test. Test. F. Really good. Control D a couple of times. Here and there. And then one there. Okay. And then we'll jump to the loop. And we'll end, what the end will mean is RTS. And then we will have an empty line and turn the listing off. Yeah, and so we are done. This is good. We're ready to save it. So we're going to hit Alt-Q to get out of full screen mode. And from here, we will assemble it. If we didn't make any errors, it'll assemble 15 bytes. Let's take a look at what it says. Okay, first off, it used the origin. So it's going to compile it. It has not compiled it. We can see that in a sec, but it's not there. If maybe we'll look, but the 300 part has these bytes. There's 15 of them in a row. So 20, which is JSR, to 58, the least significant byte of the address. FC, the most significant byte of the address, is FC58. That's basically saying jump subroutine to home. And then A2, which is load the X register direct from the next byte. That's immediate. There it is, 0A. So it's 2 bytes and it loads it into the X register. And then we're going to store the X register value, this one, to the location of 700. We reverse the bytes. Least significant byte, most significant byte. It says store the EX register, which is currently contains A, to the, which is 10. Wow, I did pick an interesting set of numbers. But anyhow, it doesn't matter. It's going to store it to 700 in the memory, which is a location somewhere around here. And then we're going to do F0, which is branch if equal. And it's going to branch to 03 bytes in the future. So it's going to skip all three of these. It's going to branch to this one, which is 60, which is the RTS. And it's going to bail. That's only if it's equal to 0. Well, it's not equal to 0. It's equal to 10 right now. Well, it's equal to 9 because it's done the decrement. And so what's it going to do? It's going to fall through to jump loop, which is the 4C, and then 0305. So 0305 is up here at the loop, stores the X, and goes through again and again and again. So that's our program, and it worked. And it's assembled, and it's ready to go. So we quit out of the editor. We can save the source. We can call it loop. We can save the object code, which is O, and yes, save. We can quit out of here, and we can BRUN our program, which is called loop. And it did it. It printed them, and it did them in the reverse order. And never mind that 10 is equal to A in hex. That's not what we're seeing here. We're seeing 0, I believe. No, sorry, 1 here, which is the inverse A. Okay, because it went 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and stopped. Okay, and it went so fast we couldn't see it, which we're going to fix here shortly. Let me go back up to this. To the beginning of the chapter, and we'll talk about it there. But basically what we've done is this first bit here. We did this loop, and then we converted it to assembly language here in this loop here. And we noted that the bytes, here they are, the bytes, we didn't look at them this way because we're in this full screen editor, but we saw it at the end of the assembly, and it, which we can get back to. So let's just go ahead and do that. Go asm, e, asm as well, and then we see that here's those bytes. All right, and they match exactly with these bytes over here. And we talked through what they meant, but we got to this one, and in this take 5 video here, I told you that 3 means to, I'm sorry, this 3 here means to jump relative. So this is branch of equal relative 3 bytes in the future. So it skips these 3 and comes to this one here. The book goes on and talks about reverse branches, reverse offsets, and it moves the end up into the middle of the file, and then it does the test, and it says branch of equal to the end, which is behind it. And he admits that that's a little bit arbitrary, and it is, but it's worth noting that then this BEQ, which is F0 just like it was before, has this weird F7 instead of 3. 3 would take it over to whatever's just past this guy, but F7 takes it back. How far does it take it back? Well, it's a squirrely deal, but if you subtract this F7 from 100 hex, you get the number 9. And then you notice that from this instruction, go back 9, takes you to this RTS, the 306. And you can convince yourself, but basically this F7 is a negative number calculated by subtracting it from 100, which is just past FF. So FF plus 1 is 100. So FF minus F7 would be, you got F8, F9, FA, FB, FC, FD, FE, FF is 8 plus 1 for 100 is 9. Wow, that's a lot of figures, right? And it's 9. And that's where we would wind up. We'd wind up back here at 306. So that's what that's about in the text. And that's kind of the next thing we would learn about from there. And then we get into the screen output using COUT. And this is, we're going to make some changes to the code and do this. This is where we start to be able to see the results a little more clearly. Because when we run it right now, it just blinks by so fast we don't even see it. It winds up at the last one. we're left kind of begging, what the heck is going on? So we're going to use this code here for our loop 2. And so without further ado, let's just edit the file we got. And we'll just change it to loop 2. And I'm going to go down to here, and I'm going to delete everything from here down, which is I'm going to use Alt, which is Open Apple, and then D to delete a line. I'm going to delete them all, except one row. So I'm going to reuse this much. May as well clean this box up. Oh, I added the 2. So we're going to hit Control D to get the box looking better. And then we'll track this code right here. And what this is going to do is, instead of printing to a location on the screen, it's just going to print the number out. So let's see if this is going to work. One can hope. It is going to work, but it's going to be tricky. All right. I'm going to go ahead and add another blank line before we start doing this. CTR we're going to create a counter. This is a label. We're going to equate the label to an address. The address we're going to give it is 06. And in the book, the author talks about, where'd it go? So we're already in the book. The author talks about the fact that these locations here, 6 to 9, are good. They're not used by anybody. So we can use 6, 7, 8, 9 without any problem for a single byte. And so we're going to store our character that we're interested in printing to screen. We're going to store it in this location. So we're going to equate it to location 06. And then we're going to set home to what we usually set it to. We're going to equate it to the routine FC58. It's really important you get those numbers right, because things will go horribly off the rails if you don't, speaking from experience. So now we're going to call this character out routine, which is provided to us by the ROM, just like the home routine, with FDED. And we'll add a blank space, and then we'll have our start of our home routine. We're going to clear the screen first. Then we're going to load the accumulator with the immediate value XFF. I'll give us 255 characters, which just so happens to be the number of characters in the ASCII character set. And then we're going to store the accumulator into the counter, into the memory location 06. Because we can't increment and decrement the accumulator in 6502. We can in the C65CO, whatever. In the enhanced 6502 we could, but we're going to pretend like, and we're going to stick to straight 6502. So we're not going to increment the accumulator. We're going to increment, oh look, I got an extra R. We're going to increment the memory location, but in order to print it, we have to have it in the accumulator. So we're going to store that in the accumulator and retrieve it from the accumulator. So we're storing, let's think about it again. So to catch up, because I talked a lot. So we have the home, we home the screen, clear the screen, and then we load the accumulator with FF. We store that value, FF, into the location CTR, which is 6, the byte that's safe from all of these different systems, integer, basic, AppleSoft, DOS, or the monitor. So nice little location, we can put this FF. So we stored it into that location. Now let's start the work of the loop, and we're going to load the accumulator from that address, because we're going to print it from the accumulator. We're going to increment it out in memory, and then we'll have to pull it back into the accumulator to print another one. So that's what we're doing. Load the accumulator from the counter. And then we jump to the subroutine that does the output of the character. And then we decrement our counter, which we can't decrement the accumulator, so we decrement the counter instead. And then we test it and say, well, if it's equal to 0, then go to the end. And that's nothing new. That's exactly what we did in the last program. And then we'll jump to the loop otherwise, which just keeps going until it is 0, and then it bends. And then at the end, we could do RTS. But if you do, you'll be really frustrated. So that's where we're going to look at the end of the chapter and read this note about BRUN and COUT. It tells us that because we're running in DOS, if we call RTS and we've done something like this character out, it's going to get confused about where to return to. And we're kind of forced to call it using BRUN because we can't do OBJ 300 anymore. Okay, so to get it to load to 300, we have to load it as a binary. So BRUN does that. So we're in this catch-22. We need to call BRUN, but if we call BRUN, we can't do RTS. So it gives us the solution right here, which is to jump to 3D0 instead of RTS. So we could do this. Let's see, let's have rover strike. You can do this as jump $3D0, but that's kind of ugly. We have a pattern that is better. So I'm going to go up here to the end of our defines, and I'm going to add another one. We're going to call it warm. And he talks about this warm reentry vector is what it is. We'll call it warm. We could call it something longer, but not. And we'll equate that to $3D0, or 3D0. And then down here, we will call warm, or jump to warm. All right, and then we'll leave it with ls. Well, we'll have a blank line first. We can do that with an asterisk. Okay, and then we can do list off. All right, which seems like loop 2 is good. 23 lines seems reasonable. I'm going to Alt-Q to get out of this. I'll type a symbol and hope it works. It did. 22 bytes, no errors. Okay, and let's parse through this a little bit. So what's going to happen when we BRUN it is it's going to load at location 300, which is the origin. These bytes, these 22 bytes. 20 means JSR, FC58, so that's home. So that clears the screen. A9FF is load the accumulator direct or immediate with this value FF. And then 85 is store the accumulator where to 06 on the at location 06. And then we're going to load the accumulator A5 from where? From the memory. Then we're going to call 20, which is JSR, on FDED, which is the COUT routine. Then we're going to decrement the counter. We're going to decrement C6, going to decrement memory. What memory location? We're going to decrement what's in 06, which means it goes from FF to FE to FD, etc. And then we got branch equal, F0, branch equal to where? 3 bytes in the future, so it skips these 3 and goes to this guy. And then if it's equal to 0, if it's not equal to 0, it's going to do this jump, FC, 4C. And where's it going to go? To 307, which is up here. It's where we load the accumulator and the start of the loop. But if it is equal to 0, it jumps to the end. And where does that go? Well, that jumps to a warm restart, 3D0. So we've assembled it. The bytes look reasonable. Let's quit this full screen editor, or if you want to, you can list it again, just to be sure what we're talking about. Then you can quit. And then you can save the source. So save it. We'll call it loop 2. Sorry, loop 2. And then O for save the object code. We'll save that as loop 2, yes. Right, and then we'll quit out of Merlin into the basic environment, and we can BRUN our new utility. If we forgot what it was, we can catalog. We can catalog D2 if we want. There it is. It's called loop 2. We can BRUN loop 2. All right, it printed 255 characters. Some of them are really obnoxious with that blinking stuff. We noticed that the loop is going backwards because we got Z, Y, X, W, V, U, U, T, S, etc., which is exactly what the author claims is going to happen. So sure enough, it worked exactly as advertised. There it is. But now we want to fix it so it goes forward in the alphabet. And I'm going to go ahead, because I hate that inverse blinking stuff, and I'm going to clear the screen. If you recall in the in one of the videos, we learned about the escape code. So escape mode also handle, yeah, that was it. It's in the basic escape mode video. But we hit escape and then shift 2, which is the @ sign, and it'll clear the screen. So that is not as annoying. But we're going to do loop 3, and loop 3 is going to do it in the correct order. But let's go ahead and kind of look at what changes we need to make. And we can read about it, but we're not going to. First off, this is the same. These 3 lines are the same. This home thing's the same, but we're going to load the accumulator with 0 now. And then we're going to store the counter. We're going to load the accumulator from the counter. We're going to jump to the cout routine. So that's all working the same. And then we're going to increment instead of decrement the counter. And then we're going to branch when that's equal to 0 to the end. Does that make sense? Branch is equal when it's equal to the end. I don't know, man. That seems like it's going to run forever. Because it's going to be 0 at the start, and it's going to be 1, 1, 1, 1, 1. We're going to do it anyway. Oh, we'll figure it out. Yeah. Okay. Let's go back into the assembly. And it goes back into 80 column mode. We're on drive 2. We still have our source loaded. Let's see what that is. All right, that's loop 2. Let's see. I think we can make some strategic changes here and just reuse this. So I'm going to change it to loop 3. Tab to get out of that insert mode. Loop 3. Control I to go back to it. All right. There it is, loop 3. The object code, that's all the same. That's the same. We're still going to use the warm start because we are going to call cout. And then JSR home, that looks good. And then LDA instead of FF, that's going to be 0, 0. So tab to go into overstrike and zeros. And then stas CTR, load CTR, JSR cout, decrement, that's going to become increment. CTR, yeah. BQ to in, jump loop. And then instead of end to RTS, we do jump warp. Yeah, seems good. All right. So with those couple of minor changes to it, I'm going to Alt-Q. Going to try to assemble it. It worked, 22 bytes. The only thing that really changed here was the A9 becomes 0, 0 from FF. And the increment becomes, the decrement becomes increment. Otherwise, it's an identical set of bytes. So we assembled it. It's there. We can queue here. And then I can save the source, but we're going to call it loop 3, LOP3. I'm going to save the object code. Yes. Going to quit. And we're going to BRUN loop 3. Okay, beep, beep. Seems like it worked twice, and they're in the right order. That's the work. It's equal to the end. Oh, the reason, okay. Wow. And he explains this in the chapter 2. All right. We're remembering that when a byte is incremented from 1 to FF, the result wraps around back to 0, 0. So when it goes around, it's counting up 0, 0, 1, 2, 3, 4, 5, 6, 255, which is FF, and then it goes again. It's gonna be 0. So that's how he trickily, wow, is that even a word? How he tricked it into working. So yay, that one works. Horrible. Let's hit escape, shift 2, enter, and now we're back to the, wow, that's blinking. Probably want to get back to normal, but we'll worry about that in a minute. Next up, we're going to do the game panel one. So I'm going to go ahead and reset this because I don't know what that blinking thing's about. But there we go. And we're here at the, we're in here for Merlin. So we can write this paddle program. And we're going to copy this paddle program verbatim, well, except for the, let's see, is there any RTS stuff? No, and there's no call. Well, yeah, there's, yeah. But it's infinite. It never ends. So when we run this program, it's going to continue running. We'll have to break into it to get it to stop. Probably have to reset the system or something. We'll figure that out in a minute. But we're going to type it in verbatim. We're going to use that joystick to mouse emulation trick to get it to capture mouse instead of the joystick. And we'll see what effect that has on our program when we run it. But let's go ahead and edit. So I'm going to go into the editor. There shouldn't be anything in it now, so we're going to go A for add. And we're going to start typing this stuff in. So Alt-8 gets us the line of asterisks. Alt-9 gets us the box. Tab takes us out of insert mode, puts us in this, and we'll call it panel. And then enter, and then we can go back to insert mode with Control-I, just to have a same kind of position. Alt-8 to get the next line of these. Asterisk for another one, asterisk. And then we don't really care where our object goes, but I think it goes about here. OBJ, $300. We'll figure out where it actually goes now. ORG, $300. Okay, and now I can Control D to delete a character, and another Control D here, and those look pretty. Okay, we can have space between those and this. We're going to create a temp variable, which is just like our counter, except we're just going to use it as a temporary storage location. Changing its name doesn't change its function particularly, but 066. Control D. There we go. And then there's pread is a new firmware function, monitor function that we're going to call that reads the paddles, and we're going to call it $FB1E. And then we got our usual home, FC58, and our newly beloved COUT, which will let us print to the screen without too much effort. An extra, whatever that is. All right. And then we'll insert a blank line before we start. So start JSR home. Okay, and then we're going to load the X register immediate with the value, let's just turn on upper strike, with the value 0, 0. And then we'll loop. And this RP read. So it's just going to constantly, we're going to set the X register to 0, and then we're going to start reading the paddles. And we'll do that pretty quickly, and then we'll store whatever we read, which comes back in the Y register. We're going to store that to our temp variable. And then we'll load the accumulator from the temp variable. This is to print it out, right? LDA temp. And then we'll JSR cout, which prints out what's in the A register. And then we'll just keep doing that forever, which is crazy. Okay, infinite loop. All right, and I think we'll turn off the listing. All right, seems reasonable to me. So basically we clear the screen, load the X register with 0, 0. We call pread, which these two statements are kind of related. You have to have the X register as some bearing on the pread. We can look and see later, but then we store the value we get back, which is in the Y register, store that to our temp, read that into the accumulator, print that out, and then do it again and again and again and again and again. So it's going to go very fast. It's not really going to wait on us to do stuff with the paddle. It's going to just start filling up our screen with gunk. And we're going to have to see the gunk versus when it actually works. But we turn the listing off after that, and we're ready to rock and roll. So Alt-Q, get us back to the high-level editor here. We're going to assemble it, see if we made any mistakes. No, seems to work I won't bore you with the byte reading here, but it's only 18 bytes long. We can quit here. We're going to save the source. We're going to call it paddle. And then we'll save the object file and we'll call it paddle, yes. And then we'll quit and we're ready to call the function. Before we do, because it's going to kind of screw us stuff, let's think about it. So I have not set up the joystick yet, but I'm going to run it anyway. But before I did that, I made sure I saved it to the floppy disk, the Merlin work disk, as paddle. And so the source code is on paddle, the binary is on paddle. So when I have to reset my machine and reboot, it's still going to be on my disk. All right, so let's BRUN paddle. All right, it fills up the screen and I start clicking and moving my mouse and nothing happens and it just prints asterisk, or no, prints the checkerboard, and it just keeps doing that ad infinitum. I think I can reset with Control F2. I think I can reset with the Apple, clicking the Apple icon over there. But another way that I might be able to do it is with Control and break. And sure enough, it worked. So I'm going to escape, Shift 2, clear the screen, come back to here. So that was nice. But let's go ahead and do the paddle trick to get our mouse to be the paddle. So instead of the keyboard numpad, we're going to say mouse. Remember that to get out, you have to click the left mouse while you're pressing control. So it is control left mouse. Anyway, there we go. And we say, okay. So now when I click into here, my mouse is in there and you can see those little white lines that move around as I move my mouse. There's 4 little indicators on the top, bottom, left, and right that you can see. Kind of if you were to draw lines between them, you would have a little cursor showing where I was. So, but anyhow, we're ready to we're going to run it again, but this time the paddle's getting mouse coordinates. So let's run it. BRUN paddle. And when we do, it's still going to fill up the screen with stuff. There we go, when we start moving our mouse. And as I move my mouse around, probably maybe when it fills up, it gets funky, but it was working. All right. And we remember to press Control and left mouse button to get our mouse back. And then, oh, wait, can we Control break? Yes, we can. Okay, so I'm going to do it again. I'm going to run it again. Oops. I'm going to BRUN paddle again. And more quickly, I'm going to move my mouse. I'm going to have my left. I'm going to hit the enter key with my left hand, and my right hand is going to move the mouse almost instantly. So here we go. I hit enter, and I start moving my mouse. You can see those characters change, and when I stop moving the mouse, they stop changing. I'm going to hit Control break. And you can imagine then that if you were to interpret those movements, those changes of the characters, instead of printing them out, if you were to evaluate them and go, oh, did he move left? Did he move right? Did he move up? Did he move down? That you could play a game with that. And we could do it with the mouse, no less. I don't know. Since we're here and we have a moment, let's go ahead and just try. Let's see, we got a Control left click. Let's try changing this back to the keyboard, the numpad, because I have a numpad. Well, let's try those keys as well. So I'm going to say OK. Going to BRUN paddle again. But I'm not going to hit enter until I'm hovering over my numpad. The numlock thing is on. I don't know if that is important. I'll try it both ways. But as soon as I press enter, I'm going to start hitting like 5, 8, 2, 4, and 6. I'm going to use the little cross. Okay. Going to hit enter and hit 8. Hit enter, 8, 5, 2, 1. Yeah, okay. It's detecting the keys that I'm pressing. And the numlock key is on. And when I turn it off, it's still interpreting it. So you could use the numlock key. Control break. Okay. Ooh, escape, Shift 2. So wow, we learned quite a bit there. And that's kind of that's it, right? I think that's pretty much it. Paddle program. Oh, we could do the transfer program to make it shorter. All right, to start editing the shorter version, we're going to get back into Merlin. I accidentally hit the pound sign, so we're going to get rid of that. And then I'll just type ASSCM. And it's back in. We'll go to drive. Let's see where we're at. We're on drive 1. Looks like I accidentally saved paddle on drive 1. We'll just work with it there. We'll save paddle 2 over to drive 2. So let's remind ourselves what the commands are. Load source, paddle. Go into the editor, and there it is. The only difference between this one and the other one is this bit here, where it says pread. We also call it pread. Everything before that's exactly the same, but now it's going to call TYA instead of what? Instead of store Y, store to the Y register. I mean, take the whatever's in the Y register, whatever we read, store that in a temporary variable, and then load the accumulator with that temp variable, and then call cout. Now we're just going to do this. We're going to read the variable. We're going to take and transfer directly from the Y register to the A register instead of going through the temp variable. And that's going to save us some bytes. So let's get started. Come down here. We just read. I guess we'll do it there. And now we're going to do TYA. Transfer from the Y register to the accumulator. And yeah, that'll do. And then JSR out is the one we want. So I'm gonna Alt D to get GSR count. Yeah, that's it. Okay. So we made our changes. We're gonna call it paddle 2 though. I'm gonna go up here and tab paddle 2. And I think that's good. We'll Alt Q as them. See if we broke anything. No. And now it's 15 bytes instead of 20. Excuse me. Now it's 15 bytes instead of 20. Sorry, 15 instead of 18. So we saved a few bytes. And our code's a little bit clearer. So all it's doing is setting up some storage space for the temporary variable, storing a handle to the paddle read function, a handle to the home function, a handle to the cout function. And then our code, which is just these bytes here, is clearing the screen, setting the X register to 0, reading from the paddles, transferring that to the accumulator, printing that out, and then doing that over and over and over. So with the new version, let's see how it's doing. We assembled it. We can queue. We're going to change drives. We're going to save the source. We're going to call it paddle 2. We're going to save the object file. We're going to call it paddle 2. And then we're going to quit out of here and we're going to BRUN paddle 2. Now let's check to see what we've got in terms of the input. Right now it's set to the mouse. So when we click in, it's going to capture it. And sure enough, there it is, it's captured. We're going to run it. And as soon as we run it, I'm going to move the mouse. Start clicking and stuff. There's click, 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 right click, move it around. You can see that it's affecting the output. Once I stop moving it, things stop changing. Control break. Control mouse click. Change it to, we'll try with the numpstick too. Sorry, the numpad. There's the numpad. BRUN paddle 2. And as soon as I press enter, I'll start pressing keys. It certainly is working. Okay. We'll break. And escape at. So that was that. That seemed to be what we needed to know. Don't forget, if you're going to be calling cout and hoping ever to return, that you're calling the warm entry vector. But other than that, that's it for this episode. Thanks.